Hi, Michael Canellis from Marvell again. And now I'm speaking to Rick Eads of Keysight Technologies, kind of one of the leading testing companies. And one thing we talked about is, at the show, people are talking about PCIe Gen 7. But as you just told me, the spec isn't even done yet.
A spec is not done.
Okay. So where are we at?
All right, so the PCI Express version 7 of the specification just finished its 0.7 review. All right, we're looking to go 1.0, right? So when is it done? Hopefully, if everything goes well, maybe mid-June. That's when we do our big developer conference. So everybody's trying to get it fast by mid-June. So that'd be great. But being at 0.7, all that means is we've kind of sort of established what the physical layer requirements are, the protocol requirements are for the silicon. So if we make any changes, then we'd have to re-release that specification. But if you're a betting person, you would say, okay, 0.7 is good enough. I'm going to go ahead.
You got to get the results and things like that.
I'm going to bet that there's not going to be any significant changes. And we're going to go ahead, 64 gigabaud, 128 gigasamples per second.
Yeah.
So that's where we are. So
how's it doing?
The spec is doing great. And what we have today at the show is we have Marvell Silicon that is demonstrating two key capabilities at 128 gigatransfers per second. The first one is we are doing a signal-to-noise and distortion ratio measurement at 128 gigabits per second, where we could demonstrate it meets the 34 dB requirement of the Gen 7 specification.
Good sign.
So this early, before we get to 1.0, we have received working silicon that meets the SNDR characteristic, which is a very difficult parameter to meet. But perhaps the more important, hold on there. I have another thing you can do. So another thing that we can demonstrate with the Marvell silicons is that if we put that device into a loopback state, we can feed it a signal that has traversed the 45 dB of channel loss at 32 gigahertz. 32 gigahertz is the channel frequency, is the Nyquist frequency.
Pretty rough road, you might.
Yeah, so we're feeding it worst case signals through this 45 dB channel, which includes the package. Now the spec limit is only 36, so we're almost 10 dB more of additional loss. So on the bottom we have the pattern generator, which is driving out a PRBS31 signal through this channel. You go from this channel, adding a lot of inter-symbol interference or loss going into the receiver of the device. So pattern generator through a channel into the receiver. So this adds a lot of distortion.
Like your bad news. Yeah, bad news over everywhere.
Trust it, because we know the chip is not going to be in a pleasant, friendly environment when it gets deployed. It's going to see a lot of ISI. So what makes the standard work are the capabilities of the receiver's equalization scheme. So you have the receiver taking in a very poorly defined signal, equalizing it, and then as best as it can, it spits it around and drives it out its transmitter to our error detector. So the error detector knows what we said. And so it's doing a symbol by symbol comparison to see, are you sending me what I told you? So it's driving a signal out, and then it's coming back into the error detector. Now the specification says you're only allowed one error in every 1 million bits. One error in 10 to the 6 bits. And what we see here is that we're achieving a bit error rate of just over one error in 10 to the 8 bits. So it's like a 45 dB channel. We're able to exceed the specification limit for the performance of the SerDes with this incredibly lossy channel.
That's great.
There might be some other impairments that we'll add, but we're not done with the spec yet. And already we're able to see that Marvell has silicon that is able to achieve some of the real critical measurements and capabilities and parameters that will be expected of everybody's device that says, hey, I've got PCI Express 7.0 capable silicon.
Excellent. Right. Well, thank you, Rick, and thank you for stress testing our silicon.
Hey,
fantastic.
thanks for coming by, and thanks for letting us borrow this wonderful device.